What's up?
Is it feasible to do the midterm in an 8-hour block?
Well, if you, assuming your simulation all goes well, I mean, you can probably complete the simulation within a couple hours, but the report, it's just like any kind of technical report, so it's going to take a while to write it. So, yeah, because it's a lot of figures, it's a lot of formatting, it's a lot of extra stuff you kind of have to write. So, I would give yourself more than 8 hours. I mean, if you're working and writing constantly throughout the time, probably, but I mean, usually with writing, you usually want to write first and then come back to it the next day and like revise and stuff. But if you absolutely have to, then yeah, probably 16 hours you can knock it all out.
I'm kind of burnt out, so it's like I can't.
Oh, I see.
I need to take the breaks where I can. So like, yeah.
I see. Yeah, I mean, technically, like if I count all the hours overall to work on the project, it's definitely going to be less than 16. But usually those are spaced out. But doing it all at once is going to be tough.
8-hour work days, that's fine.
I guess when you put it that way, but yeah, it's kind of a lot to work on, kind of just one thing over that whole time.
Yeah, I constantly do things like that at work.
Uh-huh.
I'm just on one project for like an entire it's supposed to be 6 weeks, but then like they're giving me like shorter notice time.
Oh my gosh.
So instead of 6 weeks of me finishing up a project at work, I have 3 weeks.
Oh my God. Jeez.
And then something that's 3 weeks is like 1 week. So I like, yeah, exactly. So I'm just like, every time I'm given like a break of like a couple hours, I just take it. So.
I see. Gotcha. Makes sense.
Professor.
Yes, what's up?
I'm having a problem with ANSYS.
Okay.
I have 3 errors.
Okay.
The first is solver pivot warning or errors have been encountered during the solution. This is usually a result of an ill-conditioned matrix, possibly due to unreasonable material properties, an under-constrained model, or a contact-related issue. Please check results carefully. The second is a solver pivot warning or error has been detected in ROTY degree of freedom of node 318 located in system beam extracted profile 1. This is usually a result of an ill-conditioned matrix, possibly due to unreasonable material properties, an under-constrained model, or contact-related issues. Please check carefully. You may select the offending object or geometry via RMB on warning in the message window. And the third, the mesher did not generate any nodes. All geometry may have been defeatured away.
And is this for activity 4? Is this for your midterm?
Yes, the bridge.
Okay. So the first 2 errors are well, I mean, they're probably all related. And the first 2 errors are usually just like the error mentions, it's a result of like, usually there's not enough constraints on the model. And so there might not be a fixed constraint, or there might not be, constrained enough. If you have a fixed constraint somewhere in the model, that error shouldn't be occurring. And so
I do have a fixed constraint or a fixed support.
Yes, a fixed support. Yes.
And a displacement.
Okay.
And a pressure.
Okay. Yes. So if you have a fixed support in the model and you're getting that error, usually it's due to the connections. And so it could be that when you apply your load onto the model, one of the beams or one part of the model is basically sliding off into infinity. So there's nothing keeping that part there. And so I would double check all of the connections, especially the ends of the beams. And so the ends of the beams all need to be connected to the bridge on one side, and the ends of the beams need to be connected to the bridge on the other side, and make sure the road itself is connected to the bridge and the beams as well. And so all those need to be set, and make sure that you're applying those on the right parts of the geometry too. So I would double check those connections. Usually there might be like one connection that might have been missed just because the clicking on that is a little bit precise. And so I would double check those. And if you're still getting that error, just send me an email, and then I can take another look. But that's usually the case for those 2.
Can I show you what I've got so far? Because I'm not sure what to look for, because it looks like everything's connected properly.
Okay, all right.
I
let
may
me,
have a setting that I'm not realized.
Okay. All right, let me go ahead. Let me stop sharing on here. Okay, yeah, go ahead.
Okay, let me.
Mind if I take control for a little bit?
Sure. I think I'm doing something wrong.
Let's see this one here.
Dr. Chan, can you hear me?
Yeah, I can hear you.
Sounds good.
Okay. See your mesh. Everything looks to be in order.
None of those have actually done anything. Solution is, as you can see,
Yeah. Let me try this really quick.
if that's what fixes it, I'm gonna scream.
I'm gonna try a fixed support on the other side too. Let's see.
Okay.
I shouldn't have deleted that one. I should have just left it there.
Yeah, it's fine. Because that constraint acted as a fixed support, sorta.
Right. It's supposed to anyway. Just beam extracting profiles. Top.
Yeah.
So it's the top beam that's. Okay, let me give it one more try because it is 7 o'clock here. I'm not sure. Let's try it. Let me try suppressing it really quick.
Should that beam have that problem?
It shouldn't be. What were we saying, Una?
The first search on the ANSYS forum says there's a gap somewhere in the model.
Okay. It could.
So, it could be that. do something else.
Yeah, looks like that beam right there is the problematic part. And so I would probably go back to the space claim and see, if there's a gap there or if that's, properly connected at that point. But it looks like
It looked
that's
properly connected.
I mean, the connection here is good, but I would go back and check on the space claim that it's actually, for some reason that one seems to be giving the issue. So yeah. But everything else looks okay from here. Yeah.
Okay.
Okay. All right. I need to, it's past 7, so I need to start the lecture. Okay.
Okay.
Okay. Okay, it's 7 o'clock. Let's go ahead and get started. All right, good evening, everyone. How's everyone doing today? Everyone's doing good. I have an empty room here again, but that's how it is now, I guess, nowadays. Okay, so this week I wanted to change course a little bit. So the original plan that I had for this week was that we were going to do another activity this week. We were going to do activity 5. But because the midterm project is due on Monday, so a week from today, I didn't want to start an ANSYS activity and have you kind of work on that, over the spring break as well. And so I'm going to swap things around. And so the activity we're going to do the first week after spring break, and I moved the lectures that I had for after spring break. I'm going to do it this week. So I'm just kind of swapping the 2 weeks. Okay. So this week is just going to be a regular lecture week. So we have a lecture today and a lecture Wednesday. And we're going to talk about non-linearities in ANSYS. Okay. I don't think this information probably won't be helpful for your project. This is kind of more for stuff we're going to do later. But I didn't want to overload you on too much ANSYS stuff before before the project's due. Okay. And hopefully, depends on how quickly we can get through this. But hopefully, if we get through this pretty quickly, then we can have maybe half a lecture on Wednesday where we have just kind of a project work day where I kind of help you guys kind of through just whatever issues you're having on the project. Okay, so that's the plan for this week. So hopefully, hopefully you guys don't mind the kind of the slight change in schedule. All right, and so are there any questions I can answer before we get started for today? Okay, all right, so let's go ahead and get started. Okay, so let's talk about non-linearities in FEA. Okay. All right. And so up to this point, and this includes activity 5 that we didn't do this week. Okay. Up until this point, we've basically been making the assumption that our simulations are linear. Okay. And you can think about linearity in a few different ways. So on the one hand, like the first thing that probably jumps out in your mind is we are using a linearly elastic material model. Okay. But linearity actually extends kind of beyond. Right? So let's talk a little bit about what that means. We'll talk about what that means and what it means to actually lift linearity. Okay. And so like I mentioned, linearity it has to do a lot more, with a lot more than just the material model. It kind of has more, just in general, it kind of has more to do with this idea of proportionality. Okay. And so when you can assume linearity, you really only have to run just one simulation, right? Ideally, you would want to run, part of the power of FEA is that you can run simulations under a multitude of different conditions, okay? But when you have linearity, you really only need one, okay? And as long as you're not changing the directions of the loads, you're not adding new loads or subtracting new loads, from that one simulation, you can learn a wealth of information due to this proportionality. Okay. Okay, so let me just kind of give a quick example to kind of show what I mean by this. Okay. So let's say we have a cantilever beam. Okay. And let's say that when we expose it to a certain load, so let's say 1,000 kilonewtons, the beam is going to deform, or it's going to displace by 3 centimeters. All right, so we have our beam here. We're going to apply a load. So let's say our load here is 1,000 kilonewtons. Okay. And then when we apply the load, the beam is going to bend like this. Okay. Where this displacement here is 3 centimeters. Okay. All right. So it's just an example, right? So I'm not sure what material this beam is made out of, but basically we apply a certain load, we apply an input, and we get a certain output. Okay. From this one simulation, I don't have to run another simulation. So if we assume this situation is linear, okay, if we assume linearity, I can tell you the result of the simulation if we cut the load in half. And so let's say instead of 1,000 kilonewtons, we apply a load of 500 kilonewtons. Okay. And so because of this proportionality kind of assumption here, if we cut the load in half, that means our displacement or our response is also going to be cut in half. Right, so you don't even have to run the simulation. So you can already kind of tell right away. Okay. So if we apply a load here, 500 kilonewtons, this displacement here is only going to be 1.5 centimeters, or just half of what it was before. Okay. And so, this relationship here, a large part of it has to do with the fact that we assume our material model is linearly elastic, but there's a lot of other things that are assumed linear in finite elements as well. Okay. All right. So that's what I mean by linearity. Of course, what we're talking about this week is non-linearity. And so when we assume a non-linear, or when non-linearities are present, we don't have this directly proportional relationship. And so in reality, non-linearities are always there. The fact that we're making these kind of linear, the fact that our simulations are linear is very much an assumption. Okay? So, when we say that we're introducing non-linearities, what we're actually saying is that we're making our simulations more realistic. Okay. But in a lot of cases, and in basically all the cases that we have, that we've seen so far, these nonlinearities, their effects have been fairly negligible. So we'll talk about, what are some situations where you can kind of ignore the non-linear effects as well. Okay. Okay. But in situations where they can't be ignored, we need to make sure that our simulations can pick up on these as well. Okay. And ANSYS has a lot of tools for how to pick up on these kind of large or these sources of nonlinearity. And so we're going to talk about three main sources of nonlinearities, and we're going to talk about how ANSYS kind of deals with these as well. There are more than these three sources, but these are the three main ones. Okay, so the first one, and probably the most common one, is large deformations. And so by large deformations, what I mean is basically anytime the deformations are so large that the structure distorts significantly from its original configuration. And so this is going to cause some issues that we'll talk about soon. The second source of nonlinearity has to do with topology. Okay, so we call these topologies nonlinearities. And so these are nonlinearities that result from a change in connectivity. And these are directly a result of the contact. So I'd say the most common case is when you set the contacts to be certain settings. So for our last two activities, we've seen kind of the effects of contact. So far, we haven't really explored that all too much. We've pretty much set all of our settings to be bonded. Okay. And so, this week, what we'll do is we'll talk about the different settings for the different contacts. And we'll see kind of what effect that has on the results. Okay. And number three, we have material nonlinearity. And so this kind of goes back to our material model. Okay. And so if you remember from a few weeks ago when we talked about material properties, we talked about how there's different models out there. So things like hyperelasticity. When you introduce those, then that introduces nonlinearity in the material properties. Okay, so we're going to go through all three of these different causes, kind of what you can do about them and what features ANSYS has to simulate them. Okay? But before we jump into that, I want to kind of preface this by saying, when you introduce nonlinearities into a problem, not just FEA, when you're talking about any kind of engineering or applied math problem in general, nonlinear things are always much more difficult to solve with linear. Okay. And so don't take this decision lightly, right? And so, for the scale of problems that we're doing in this class, you're probably not going to notice that big a difference, right? Which is kind of the theme of this whole class, right? So, with the student version, there's only so many elements that we can do, but making this decision to go with a nonlinear solver or adding nonlinear components to your simulation, it shouldn't be taken lightly. Right? And so if you're going to decide to do that, just like anything, just like any decision that you make in FEA has to be properly justified. So you have to have a good reason to want to include these nonlinearities. Maybe you're expecting very large deformations. Maybe you're expecting the connectivity or the contacts to kind of break down, or maybe you need a nonlinear material model. Okay.
Dr. Chan, I have a question.
Yes.
When you say non-linearities problems are more difficult to solve, does that imply that the problem itself is very cumbersome, or does that apply, or does that mean that it's computationally expensive, or is that the same? It's the same thing, right? If it's computationally expensive, that means it's hard to solve.
Oh yeah, no, they're the same thing. And so, for a user, from a user's perspective, the big difference that you'll see is mostly in the cost. And so if you turn on nonlinearities for your simulation, then the simulation is going to take sometimes a lot longer to run than normal. But on kind of the back end, for the equations, turning on nonlinearities means that a lot of times you're changing kind of the nature of the equations themselves.
Non-linear situations are more realistic. Is that fair to say, or is that not fair to say?
Yeah. So I mean, there's when you're adding nonlinearities, you're basically adding more complexity to the governing equations. And so in general, in general, I would say when you're adding more complexity to a governing equations, you're doing that. The reason you're doing that is to make it more realistic. And so you're adding kind of extra effects. You're adding kind of additional.
I see what you're saying.
That is not present in the original equations. And so
it's less modeling, less assumptions.
Exactly right. So you're lifting a lot of assumptions, and so and a lot of times, sometimes these additional terms they don't add a significant amount. Maybe they handle mostly edge cases, maybe edge situations, but they are important. And so including these terms does make it more realistic.
Sounds good.
Yep. Right. And so, when you're adding these nonlinearities, definitely you want to justify it as well. Okay. Just like any other kind of FEA decision that we make in this class. And so, with that said, for the midterm project, I don't think you don't need nonlinearities unless you come up with some very crazy loading scenario. And so I don't expect, many people to use that for the midterm project, but if you do, you make sure you justify it. Okay. Any questions on this so far? Okay. All right. So let's expand on each of these three kind of sources and talk about kind of why they introduce nonlinearities. Okay. So let's start with large deformations. So when you have large deformations, just like I mentioned above, your mesh and your geometry is going to be significantly distorted compared to where it started. Okay. It's actually something that's quite unique. And so, it's not something that I really kind of appreciated until I actually started working here, because my background actually is in mostly fluid-based FEA. And so the thing about fluids FEA is that your mesh is always fixed. And so, you don't really move the mesh, right? For solids FEA, or for structures FEA, the mesh actually changes and it actually distorts along with the deformations that you solve, okay?
Dr. Chan, I have a question.
Yes.
When you say fluids FEA, is that something completely different than computational fluid dynamics, or is that what you're implying?
It's CFD. I mean, I consider
Okay.
it CFD, but there's different ways that you can run CFD. And so I think the most common way is to use finite volumes,
Yes.
but you can also do a finite element based CFD.
Oh, I see.
That was kind of my research.
Sounds good.
Right. And so when your mesh and elements get distorted, we just kind of spent a lot of time talking about, that's usually something you want to avoid. Okay. And so when these distortions and when these element kind of distortions get so bad, you could have situations where, your solution starts to get bad as well, because your elements are getting, very skewed compared to before. Okay? Because you could have a situation where, maybe you work really hard to get a mesh with elements that look very nice. And so maybe you start with an element. I'm going to do a 2D case because, I'm drawing on a two-dimensional iPad here. Okay. And so maybe you work really hard and you've got elements that look like this. So this is a very nice looking element, right? So straight parallel edges, 90-degree angles, very, very high quality element. Okay. But let's say that you apply a load onto this element here, or onto the structure overall, such that the element starts to distort. So maybe, you apply a load and it starts to look like this. And maybe you apply it so much and the element kind of distorts, and it kind of looks like this after all. So that's obviously very bad. And so, after you apply your load to this, and let's say that you want to compute something like a stress on this element, you're going to have a hard time. You're going to have kind of a lot of those kind of after effects of a poor mesh that we talked about last week. And so in some extreme cases, and so, let's say that you have a case where the distortion is really bad, you may have to do what's called dynamic remeshing. Because sometimes you'll have situations where you apply a load and your and your structure is going to deform so much that it might as well just be a whole new geometry. Okay. And so in those situations, you may have to just kind of just make a new mesh, when your deformations get so bad. Okay. You typically want to avoid this because remeshing is a very, very expensive process, especially for much of the very heavy duty meshes that are in like the millions or tens of millions of elements. But that is an option, and there are some problems out there where remeshing that's kind of your only recourse, and so that's the only thing that you have to do. Okay? The nice thing in ANSYS is that it's built in fairly, I'd say fairly well, and so you can remesh. It's just not a it's not a good thing to do. I had a student that he just finished last semester. He was working on a problem for me where he was experimenting with the remesher a bit. But even for a very simple problem, the cost got so extreme that it just was not feasible for even the simple problem that we were looking at. So yeah, it is possible, but a lot of times you need kind of a supercomputer for that. Okay, but one way you can deal with this, at least for static problems, which is kind of the majority of what we're doing in this class, one way that you can deal with this kind of geometric nonlinearity is to apply the load in steps. And the good news is that ANSYS actually does this kind of automatically already. And so I'm not sure, maybe some of you have noticed, but if you ever clicked on one of the loads that you're applying in one of your ANSYS activities, if you look in the bottom right of the screen, you should see kind of a ramp that kind of goes up. Okay. So that's ANSYS's way of kind of slowly ramping up the load until you reach the final kind of the final configuration. Okay. So oftentimes you're going to see something like this, where on the horizontal axis we have time, and on the vertical axis we have load. Okay, and so you'll see ANSYS do something like this, where it kind of ramps up like that. Okay. And so ANSYS does this, automatically for a few different reasons. It's not just for large deformations. It helps a lot with stability, and so it helps to make sure that your simulation kind of finishes in the most stable way possible. Okay, but it also helps with this kind of large deformation as well. Okay? Because when you start to have non-linearities, what you start to see is that this kind of relationship between load and response, or load and deformation, or load and stress, does not really follow this linear model. And so for a linear case, you might have something like this. And so on the left here, I'm going to have time and load. And right here, I'm going to have time and deformation. Okay, so for the load, we're going to ramp that up linearly. So it's going to look like this. Okay. And then what ANSYS is going to do, it's actually going to apply the load in kind of small increasing increments. Okay, so we're going to start with a load of 0. And ANSYS knows here, this is your final load right here. So this is the load that you're actually applying inside ANSYS. Okay. And what ANSYS is going to do is then ramp up slowly to that. And so, maybe here we're at 10% of the load, maybe here we're 25% of the load, 50%, 75%, 90%, and 100%. Right, and each one is actually successive simulation. So each time the load is increased, ANSYS is actually running a simulation in the background to compute what the deformation would be. Okay. Okay. And so if you had a purely linear simulation, you would have a graph that looks like this, right? And so for a linear simulation, as you ramp up the load, the deformation or the response is also going to ramp up linearly as well. Okay. But for a nonlinear simulation, you're going to see a behavior that kind of more is like this. And so maybe for the smaller values of load, we're going to mimic the same ones. But then as you get to the higher values of load, you're actually going to see it deviate from this this curve. And so typically what you'll see is that when you introduce nonlinearities into the problem, the computed deformations that you get actually increase.
So Dr. Chan,
Yes.
so is it safe to say that in a linear FPA analysis, the loads are linearly related to the deformation? The relationship is linear. Is that what you're trying to apply here?
Yep. Exactly. Yep.
What about, so we just said that the load is linear to the deformation. What about the stresses? Are the stresses linear to the load?
Yes. Typically they are, yes, because because of that proportionality thing that we talked about at the beginning of class today. So I'm using deformation as an example here because that's usually the most apparent one that you can observe. But this relationship also works for
stresses.
Yeah. Mm-hmm.
I see. And then another thing that I'm comprehending is that what you're saying from drawing those graphs is that for nonlinear analysis, the deformation increases with time, but in a nonlinear way. Is that?
So I'm using time here because we're applying the load gradually over time.
With each time
so
step.
It's exactly so each dot that we have here, we're increasing the amount of load. And so it's not necessary that nonlinearity makes deformation change with time. It's more the relationship between the load and the deformation. And so I'm using time as an axis here just to kind of show you how the load ramps up and how that actually changes the response.
I see.
Mm-hmm.
Thank you, sir.
Yep. And so the reason for this is interesting. And so, if you, if you recall from our discussion of from advanced meshing, is that, as your elements tend to get more and more distorted, it tends to kind of stiffen up your system. Yeah. Of course, this effect is most pronounced when you have a linear element. And so when you have linear tetrahedra or linear hexahedra, you see that very pronounced. And so we have the what's it called? The shear locking effect that we talked about before, right? But even for quadratic elements as well, it kind of has this effect. It's just not as pronounced. Okay. And so what you're doing, so when you tell ANSYS that you want to run a nonlinear simulation, ANSYS becomes a lot more careful about how it ramps up the load to try to kind of maintain as much mesh quality as it can. Okay. Right. So what you'll see, and you can start to, and you can kind of actually already turn this on for your midterm project as well. If you're still working on activity 4, you can see this as well. Under analysis settings for your solution, there's a toggle for large deformations. You can either turn it on or off. And so when you turn it on, ANSYS will kind of ramp up the load a lot more carefully, try not to kind of distort your mesh as much as it can. Okay. I will say that, for a lot of our activities, unless you really kill it with a very large amount of load, you're probably not going to see a big difference between, the results without large deformations and the results with large deformations. But that's basically what's happening under the hood. So when you turn on large deformations, ANSYS is kind of really being very careful about, when you apply the load, how much are the elements distorting? It doesn't need to do it kind of in a more intelligent way. Okay. And you can modify this manually too. And so if you want to modify how many steps or how many increments that you want to ramp up the load, you can do that as well. All right, any questions on this? Okay. All right, let's take a quick detour before we move on to topology nonlinearity, and let's talk about nonlinear convergence. Okay. One of the unfortunate things about FEA is that we use the word convergence a lot. And so I know we've been talking about mesh convergence a lot, and that's the most important convergence that you should know about. So mesh convergence is you know, that's the main thing, but there's other things as well. Okay. And so one other convergence that we can talk about in this class is nonlinear convergence. Okay. Okay. And so, like I mentioned before, you know, when you introduce nonlinearities into a problem, you know, it changes the governing equation, especially when you get into material nonlinearities as well. Okay. And so when you change the equations, you know, sometimes that means you have to change the method that you use to solve it as well, right? And so the main change that happens underneath the hood for ANSYS is that it changes our solution method to something called the Newton-Raphson method. So Newton-Raphson is a very common method. It's used a lot in code because it works so well for nonlinear problems. We're not going to get into the details of that method. That's a totally different class. But I will tell you kind of what it aims to do. Okay? Basically, you know, the way Newton-Raphson works, it works, you know, specifically for nonlinear equations. The way Newton-Raphson works is that it linearizes it. So it approximates the nonlinear terms with linear terms.
Dr. Tran, I have a question. Please let me know when it's good to speak.
Yeah, you're good.
Okay. One thing that popped up into my head when you wrote that Newton-Raphson vocabulary in your notes is explicit solutions and implicit solutions. Excuse for the car alarm in the background. However, back to my point. So is explicit solution a linear solution and implicit solution non-linear solution, or are those related somehow, or am I just thinking about something completely different regarding explicit and implicit?
Yeah, so explicit, implicit, that more has to do with time stepping methods, and so you're definitely on the right track. They share a lot of similarities. Newton-Raphson is more specifically for nonlinear equations. And so, you know, usually actually the way it works, and so you know, you're kind of jumping ahead a little bit too. So, you know, implicit.
Yeah, I'm just confused because I know that the Newton method to solve a implicit equation is to get a solution and just reiterate, resolve. But you're saying that the Newton-Raphson method is used for nonlinear convergence, and is that the same? Is that almost the same thing, or?
It's the same idea. And so, you know, for both the Newton method and Newton-Raphson, you start with an equation, and you're essentially trying to find the null solution or the root of that equation. Just the way that you do it is a little bit different because Newton works specifically for linear equations. Newton-Raphson basically makes a modifications for nonlinear equations. So that's why it's kind of named after both. So actually, the guy that actually came up with it was actually Raphson, but it was you know, he based the
You base
method
it on-
around the Newton method. So that's why both are kind of credited for this method.
Okay, and explicit and implicit have to do more with the time steps.
Exactly right. So that have more
Okay.
has to do with unsteady problems. So that's actually the subject for activity 5. And so we'll talk about explicit, implicit after the spring break.
Okay, sounds good, sir.
Yep. Okay. And so the way Newton-Raphson works is that it basically approximates the solution or approximates the nonlinear terms with linear ones. But of course, this is going to incur some errors, right? Whenever you take a nonlinear situation and you assume that it's linear, just like we've been talking about the rest of today, there's going to be some errors associated with it. And so the way that we compute these errors is that once you've basically approximated those nonlinear terms with linear ones, it then becomes a lot easier to solve that equation, right? But if you then take your solution to that equation and plug it back into the nonlinear form of that equation, you're going to get some discrepancies. Okay? I should say plugging in. These errors, we can quantify these errors. And so usually these errors are kind of averaged across your entire mesh, okay? And so these errors we give it a specific name called the residual. And so sometimes you'll hear the term residual kind of show up when you're talking about computational methods just in general. And so usually the residual has to do with, basically the Newton-Raphson method. And so you have kind of a linearized solution to a nonlinear problem, and you want to see what are the discrepancies. Discrepancies are the residual. Okay, and so when we talk about nonlinear convergence, we basically want this residual to go down as we iterate on the Newton-Raphson method. Because the way Newton-Raphson works is that you don't just do it in one step, right? And so the way it works is that you do this, you apply this linearization, you get a solution, you get the residual, and then you use that residual to actually improve your solution, right? So it's a very iterative process. And so you do it once, you get a solution, you try again. So that's kind of where the Newton part of the Newton-Raphson comes in. Okay. And so when we talk about nonlinear convergence, we're talking about this idea that we expect the residual to go down. Okay. And so ideally, the residual should go down below a certain threshold that we can say that our solution is accurate enough. Okay. And so you can actually plot this. And so if you have nonlinearities turned on in your problem, whether that be from large deformations or topology or for the material properties, you can actually view the nonlinear residual. Okay. And so if you go to solution information in ANSYS, solution information, and then you go to, you can do one or two. So you can either do force convergence or displacement convergence. What you'll see is a plot that looks like this. Right, it won't look exactly like this, but this is just kind of one example. Okay. Right, so hopefully your solution looks like this, where this right here, this dotted line here would be the threshold. And this line right here is the your residual at different iterations of the Newton-Raphson method. Okay. Where each data point right there is a different Newton-Raphson iteration. So that's one good way to check, because one thing that can happen is that when you introduce nonlinearities, maybe you're introducing a little bit too many of them, is that your solution may not be converged. And so it's a good habit to check when you are introducing nonlinearities, is to make sure that you're still getting good nonlinear convergence. Okay. So again, this is different than mesh convergence. Mesh convergence is a different thing. But you want to make sure that your whatever finite element solution that you have is converged on all fronts. Okay, so every type of convergence, you want to make sure that you're converged, right? So that's kind of the idea for FEA. Okay, any questions on this? Okay, all right, so let's talk about topology nonlinearity. Our question is, how would we check that it's converged again? Yeah, so you would just go follow this this process here. So you would go to solution information from ANSYS mechanical, and then from solution information, you would check either the force convergence or the displacement convergence. Yeah, and so you should see a plot that looks like this, and so you should see something that kind of goes down with time. Yeah. Mm-hmm. Okay. So topology nonlinearity. So this, again, this more has to do with the contacts between different parts in an assembly. So far, we haven't really dealt with this, because whenever we have contacts between different parts, we usually assume that the parts are bonded together. Okay, and so when they're bonded, when you set a bonded support, you basically are assuming that even though you have different parts in an assembly, they're going to behave as one because they are bonded together. Okay, but if you kind of loosen up this assumption here and you allow parts to slide or even to separate, then you can introduce some nonlinearities into the simulation. All right, so I'll do a quick example. Okay, so let's say we have a two beam system. Maybe one beam is like this, and it's propping up another beam. that. Okay. And so right in between these two, we have a contact. Right? Right. And so for the case when the contact is bonded, and so, let's see if these two parts are bonded together, when we apply a load here, okay, so let's say we're applying a load vertically up top like that, and that contact there is bonded, then this whole structure kind of behaves as one, okay? Versus, let's say that we allow these parts to separate and to slide. Okay? So let's say that we apply a load up top. So just like before, we're going to apply a load up here. What can happen is that if this contact here slid, okay, what's going to happen is that this, you can kind of imagine, so you're applying load up top, then this beam here is going to rotate down this way if it's kind of sliding and it loses that contact there, okay? And so if this beam kind of slides down like this, it then loses contact. And so kind of the geometrical support or just the structural stiffness of this entire assembly as a whole is going to change if that slides, right? And so maybe this only happens for certain values of the load. And so for a light amount of load, maybe the separation doesn't occur and this can still behave as one kind of part. But as you increase the load, maybe that increases the amount of kind of tangential force that the left bar experiences, and then eventually it kind of separates, okay? And so you have this kind of, again, you have this kind of non-linear relationship of load versus deformation, okay? So at one point you might have kind of an abrupt big change in the amount of deformation that you see. Okay, and so with that said, let's talk about all the different contact options that you have within ANSYS and talk about whether they introduce non-linearities or not. Okay, so there are 5 that I want to go over. Okay, so the first one I want to go over is bonded. So this is the one that we have been using. So we've been using this one in activity 3 and activity 4. Okay. And so when you have a bonded support, that means the two parts or the two contacting regions of the two parts are completely bonded together. So their deformations are the same, or they're going to be matched together at their contacts. And so what we say is that they're coupled together in both the tangential and the normal directions. Okay? So no sliding, no separation. And so of course, with the bonded contact, the bonded support, this does not introduce any kind of nonlinearities. Spell right now. A weird double negative there. No nonlinearities. Okay. All right. Next, we have no separation. All right. And so under no separation, the two contacting regions are coupled only in the normal direction. Okay. But they are allowed to slide past each other by a small amount. So it's not that much. And so there are still some constraints in how much they can slide, but they are able to slide. Or at least that's the assumption. The assumption is that, the sliding is very minimal relative to the overall deformation of the entire structure. Okay. All right. So effectively speaking, on a kind of a grander scale or kind of a more overall scale, effectively there's no big amount of sliding. Okay. And so because of that, because there's no big sliding and there's no separation, then this also does not allow any nonlinearities. All right, number 3 is rough. And so a rough surface, that's when the two surfaces or the two contacting regions are allowed to separate. But a rough surface means they can't actually slide. So absolutely no sliding is allowed. And so this is meant to kind of represent the case when you have two things that are, maybe they're both have very rough surfaces. And so the coefficient of friction is so high that they physically can't slide past each other, at least not with a significant amount of force. Okay, but they are allowed to separate. Okay? And so you can almost imagine, two soft tooth surfaces that are going to interlock with each other. Okay. And so this is the first case where we do allow, this does introduce some nonlinearities. Okay? Because when surfaces are allowed to separate, or when regions are allowed to separate, and if separation does occur, that dramatically changes like the overall stiffness or how the overall structure can handle any kind of response. Okay? All right, so that's the rough surface. Now let's go over frictionless. All right, so under a frictionless surface, this is the least constrained option here. So you can almost think of it as the opposite of bonded. Okay. And so the contacting regions, they're allowed to separate, and they can slide past each other freely with large amounts of slide. And so, of course, because these surfaces can slide past each other a lot, and they're allowed to separate. If these do occur, it does change the overall stiffness of the model. And so this, of course, introduces non-linearities. All right, so last one. So this is number 5, and then we'll pause for questions. Okay. So the last type of support that we have is frictional. And so frictional surfaces, the contacting regions are allowed to separate. And so right away, you can already tell that this is going to introduce non-linearities. Okay. The difference between this one is that under a frictional surface, the regions are allowed to slide past each other. But it's not as free as the frictionless one. And so the sliding, the amount of sliding and kind of the speed of the sliding depends on the coefficient of friction that you have to introduce yourself. And so you have to, the reason this one is last is because it requires kind of some extra information compared to the previous ones. So this one, you have to input the coefficient of friction. And so ANSYS is not smart. It might be, and maybe kind of the more advanced versions of ANSYS. Even when you select different, certain materials for your parts, you still have to input the coefficient of friction. And normally that's something that you want to do anyway, because if you have kind of a rougher surface, or maybe you kind of sanded a surface down, or maybe smooth it down, you want to be able to have that coefficient of friction. So make sure that you input that if you're using a frictional support. And this, of course, introduces non-linearities. Okay, so those are the 5 types of contacts that you can run in ANSYS, and that's kind of the difference between them. Okay. For most of this class, with one exception, being activity 5, we're going to be mostly using bonded supports just because that's kind of the easiest to work with. But I did want to make you aware of the other ones, especially if you want to use different contacts for your final project, which again we'll talk about after this. Okay, any questions on topology nonlinearities here? Okay, so one last thing I wanted to cover today before we close it out today is how ANSYS deals with when two regions penetrate each other. Okay, and so no matter what type of contact that you choose between different parts, you know, ANSYS makes it impossible for one part to push into the other one. Okay, which, you know, is physically impossible, right? If you have two parts, you have my glasses and my pen here, right? Like unless, you know, unless we live in the virtual world, there's no way for my pen to phase through my glasses, right? So the way this is enforced is that ANSYS basically does a check. So when you have a contact between two different regions, basically it's checking to make sure that the nodes of one part are only contacting the nodes of the other part only on the surface. And so there should never be a case where the nodes of one part are inside the nodes, the body of another part. Okay. And so one example, you know, let's say we have a triangular part here. We have kind of a square block here. Okay. Right, ANSYS is always going to make sure that even if you have a load that's pushing it this way, okay, that triangle never actually pushes into that square. Okay, which may seem like a very obvious thing, but when you're running kind of these very complex simulations with very, you know, lots of parts, this actually becomes not so trivial because you're kind of individually. You could think about it, you're solving individually for the deformations for each part, and unless you directly account for this for the other parts, you know, you may have one part phase into another. Right, and so what you don't want to happen is something like this. So you have a triangle, and it kind of pushes into your block just like that. Okay, so this is, you know, X from the face. Okay. You know, and it sounds trivial. So the first time someone told me this is that, you know, you can't have two parts penetrate each other. It's like, yeah, duh. You know, that's obvious. But, you know, once you start getting into the mathematics and kind of the methods that actually you need to do to make this happen, it's actually really complicated. Contact is really hard. Actually, it's something that I know about it kind of on a surface level, but the actual mathematics is actually quite difficult. The algorithms are quite difficult. So. But ANSYS makes it really easy, so you don't have to worry about it when you're using ANSYS. All right, any final questions before we wrap it up for today? Okay, all right, so that's all I got for today. And so on Wednesday, we'll pick this up. We'll
Can you hear me, Dr. Cha?
Yes, I can hear you.
I do have a question about homework.
Okay, let's I'll answer homework questions after this. Yeah.
Sounds good.
Yeah. Yeah, so on Wednesday, we got maybe about halfway through, so I'm hoping we can finish a little bit fast on Wednesday, because I would like to have a little bit of time to talk about your project. So if you have kind of issues with the projects and you can't make it to my office hours, I do want to reserve a little bit of class time for it, but we'll see how quickly I can get through the stuff on Wednesday. All right, so thank you guys for coming today. I hope you guys have a good rest of your night. If you have questions on activity 4, I'll stick around for another maybe 15 minutes to answer questions on those. But if not, I will see you guys on Wednesday. Yeah. So I'm changing the schedule a little bit. So I'm going to change the Canvas site. So we're going to do activity 5 after spring break. Yeah. Okay, Ivan, you had issue. Oh,
Yeah, you pretty much just answered my question. I was gonna ask if we were gonna get assigned activity 5 on Wednesday, but you just said after spring break.
yeah, I'm not gonna assign until after spring break.
Sounds good. All right then, sir. Have a good day.
Thanks, you too.
Have a good night.
Yep. You too.
Professor,
Yes.
still having problems with ANSYS.
Okay.
If
hang on.
I,
Our monetary asked question is thus coming week spring. Yes, next week is spring break. Yes. Yeah, so we don't have any class next week. Next week is spring break. So that means the project is due on Monday. So a week from today. Yeah. Yep. Chris, I have one question in the class and then I'll answer him and then I'll come back to you.
okay.
This is the problem 7. Yeah, so what I've done is, like you just told us to do it without sharing it, right? So what I did was I just meshed it directly.
Yeah.
I got the meshes, but the next one story I've gotten error. Is that fine?
Yeah, that's fine. So the problem 7 is the solid.
Yeah, it wasn't working. right?
Yeah, that's
some huge
that's-
error kept coming.
that's what I expected. So this geometry is very challenging on purpose.
Yeah.
And so if you actually do get a result from the solid elements, that's more amazing than if you don't get a result. So
Oh,
So
so I
if you
don't know. When I was doing it these, it didn't work. So
okay, yeah, if it doesn't work, receive me an error, just report.
Okay.
Cool.
that's,
Okay, cool.
thank you.
Yep. Yep.
So the midterm, I says one of the charts which they use in the disk arrow, the single disk arrow.
Okay.
So based on that, I try to do the simulation. So pretty much have this, like, could I use that simulation, like consider it as the disk arrow?
Oh, yeah,
part
yeah.
of the shaft?
Yeah, no, that's fine. That's fine. Yeah.
I just want to confirm, yeah.
Yeah, anything that you can think of and it makes sense. That makes sense to me. So yeah.
Thank you.
Yeah. All right, Chris. So you're still having issues with the
Yeah.
okay.
I opened up claim space or space claim and looked at it. I'm not seeing any issues. I went through the instructions again. Everything looks, I can't make heads or tails of this.
Okay, you want to share your screen again?
Yeah.
Thanks, you too.
I even went through repair and did, all those stitch and gap and check those out. And
I mean,
the only
this,
thing yeah, I checked everything I could think of.
yeah, so I mean, this beam right here is the one that's causing it.
Yeah,
Um,
but I don't know why or how.
your guess is as good as mine at this point. Let me see. I wonder if we move it. Let's try moving it and see. Let's try moving it up to here. So when you do. Okay. Let's switch back to mechanical. Let's see.
Okay.
What I'm going to try to do is I'm going to try to separate the support. And so just to kind of help debug the issue, I'm going to change your contacts so that the bottom beam is going to have their own contact region, and then the top beam has its own as well. See what that does.
Oh, yeah, it was still doing a bunch of weird stuff. Okay.
It's still loading.
Yeah.
Oops.
It should be loaded.
Okay, I'm gonna stop.